Hey there, and welcome. Today, we're going to put on our detective hats. Our case? It's the huge, sprawling, and frankly, sometimes chaotic world of the animal kingdom. So let's start by getting a sense of the sheer scale of this investigation. Right off the bat, you can see the size of the challenge. Biologists have already described and named over 1 million species of animals, and that number is still climbing. Think about that, over 1 million different ways to be an animal. It's an absolutely staggering number. So that's the big mystery, right? How do you even begin to sort through all of that? How do you make sense of millions of different creatures? Well, it's not just random guesswork. There's actually a method to the madness, a system of clues hidden right inside each animal's body. To solve this puzzle, biologists have this, well, it's kind of like a forensic toolkit. They ask a few fundamental questions about how an animal is built. And these aren't just trivial details. They're deep clues that tell us a ton about that animal's evolutionary story. The first question is all about the basic blueprint. Are we looking at just a loose pile of bricks, or are those bricks organized into a fully built house? You know, sponges, for example. They're at the cellular level, basically just a simple clump of cells working together. But pretty much every other animal takes it way further, organizing cells into tissues, organs, and complex systems. All right, our next clue is all about the animal's overall design, its symmetry. Think of it like looking at the floor plan of a house. How are all the parts arranged? This basic pattern actually reveals a surprising amount about how an animal lives and gets around. And really, there are two main options. Over on the left, you see radial symmetry, like in this sea anemone. You can slice it through the middle a bunch of different ways and still get mirror images. This design is great for animals that just sit in one spot, waiting for food to drift by from any direction. But on the right, that's bilateral symmetry. There's only one way to slice it to get two identical halves, a left and a right. This is perfect for animals on the move, with a clear head end leading the charge. Okay, now we're digging a little deeper, looking at the raw materials an animal is built from. When an embryo develops, its cells form layers. Simpler animals, what we call diploblastic, have just two, but more complex animals are triploblastic. They've got a third, crucial layer in the middle called the mesoderm. And that middle layer, it's a total game changer, because that's what you build complex organs out of. And having that middle layer, the mesoderm, opens up a whole new possibility, an internal fluid-filled body cavity we call a column. This space is so important. It gives organs room to grow. It acts like a shock absorber. Really, it's a huge deal. So whether an animal has this cavity and how it's made is a major fork in the road for our investigation. And when you look, there are really three possibilities. An animal can be an acolomate, meaning no body cavity at all. It could be a pseudocolomate with a kind of false cavity that isn't fully lined by that special mesoderm layer. Or it can be a true colomate with a body cavity that is completely wrapped in mesoderm. This diagram really shows the difference perfectly. Look at C, the acolomate. It's just solid tissue right through. Now look at B, the pseudocolomate. You see that cavity, but notice the mesoderm layer is only on one side. But now look at A, the true colomate. See how that body cavity is completely surrounded by the mesoderm? That is the key distinction we're looking for. Okay, so we've gathered our forensic tools, right? We're checking levels of organization, symmetry, germinal layers, and what's going on with the cocoelom. Now it's time to use these clues to put it all together and build our tree of life. And here it is, our roadmap. I know it looks a little complicated, but it's really just a logic tree. Just follow along with me. We start on the far left with all animals. First question, levels of organization. If the answer is cellular, we follow that top branch right over to phylum Porifera, the sponges. Done. If it's tissue/organ system, we head down. Next question, symmetry. If it's radial, we branch off to the jellyfish and their relatives. If it's bilateral, we just keep going down the main line. Every single animal has its own path on this map. So, just like we saw in the chart, every investigation starts right at the base of the tree with that first big question. What's the fundamental level of construction here? If the answer is cellular level, which means the animal is really just a loose collection of cells with no true tissues, our investigation takes us straight down one branch to the phylum Porifera, the sponges. Case closed for them. They're basically the simplest multicellular animals around. But if the animal does have true tissues, well, that takes us down the main trunk of the tree. And that's where our next question comes in. What's its symmetry? This single clue splits the investigation again, separating the radial animals, like jellyfish, from all the bilateral ones, like us. All right, now that we kind of see how the logic works, let's open up a few case files. Let's look at how these rules apply to some of the major groups, the key players in our animal kingdom lineup. First up, the flatworms. So let's run them through our checklist. They have bilateral symmetry, check. They're triploblastic, so they have all 3 germ layers, check. But, and here's the kicker, they are acolemate, no body cavity. And that's exactly what keeps their body plans so, well, flat. Next in the lineup, we've got the roundworms. They're also bilateral and triploblastic, but they took a different evolutionary turn. They developed a body cavity, but it's what we call a false one, a pseudocoelom. It might seem like a small step, but it allows for a much more complex tube-within-a-tube body plan. And now for the undisputed champions of the animal kingdom, the arthropods. I mean, this group has it all. Bilateral symmetry, a true column, plus their signature moves, a hard exoskeleton and jointed legs. This incredible toolkit let them conquer basically every habitat on Earth, land, sea, and air. It's why this one group makes up the vast majority of all known animal species. It's not even close. Coming in at a very respectable second place is the phylum Mollusca. They're also true collimates, but with a totally different take on the body plan. They usually have a soft body with a big, muscular foot to get around, a lump of organs called the visceral hump, and very often a hard shell for protection. Okay, get ready for a fascinating plot twist in our investigation. Meet the echinoderms, like this starfish. What's so wild about them is that they kind of live 2 different lives. Their larvae actually start out with bilateral symmetry, just like we do. But as they grow up, they go through this radical change and become radially symmetrical adults. It's a really unique evolutionary puzzle. So after following all these clues and building this tree, what have we really learned? What does this whole system of classification actually tell us? Because it's a lot more than just a fancy filing system. You see, this tree of life isn't a filing cabinet, it's a family tree. It shows us the deep evolutionary connections between all animals. Those simple questions we've been asking about body plans, they let us map out the grand story of evolution, where every new feature, every new branch represents a major innovation, a new way of living. It's an incredibly powerful framework for understanding not just the animals alive today, but all animal life that has ever existed. And you know, this investigation is far from over. This blueprint is always being updated. Every year, scientists discover new species in the deepest parts of the ocean or the most remote jungles. So the final question is really for you to think about. As we keep exploring, what new strange features will we find? And where will the next unexpected branch on this incredible tree of life pop up?